Good afternoon, and welcome to our Thursday afternoon colloquium series. It's my pleasure today to introduce Professor Mona Jarrahi from Electrical Engineering Department at UCLA. She received her PhD from Stanford University in 2007, and after that she was a postdoc at Berkeley for about a year. Then she moved to University of Michigan at Ann Arbor as an assistant professor. But recently, about 2 years ago, she moved from there to UCLA, where she is now an associate professor of electrical engineering. She has received many awards. I'm going to mention a couple of them. She has received the Presidential Early Career Award, Young Investigator Award from Army Research Office, Office of Naval Research, and DARPA. And she has also been named the Kavli Fellow by the National Academy of Sciences. She works in the area of terahertz and millimeter waves, sources, and sensing. And she's going to tell us about her research today. Please welcome Professor Jarrahi.
Thank you very much, Professor Masood. And I also thank you for your kind invitation. It was a pleasure to be here. Today I had a lot of exciting discussions with faculty and found a lot of exciting collaboration opportunities. So thanks for making it possible. So today I'm going to talk about some of the research advancements that we had in the past few years, and mostly focused around terahertz technology. So I give a very short introduction about our motivation to work in this field, some of the fundamental and practical physical limitations we face, and then I list some of the, depending on how time allows, some of the techniques that we use to bypass these limitations. Mainly I focus on how using plasmonic photoconduction helps us to achieve higher efficiency terahertz sources and higher sensitivity terahertz detectors, and also multispectral sensing, and also how reconfigurable metamaterials allows us to basically create novel passive terahertz components like modulators, tunable filters, and beam steering devices. I cannot dig into all the topics. I have chosen some sample devices that have been in this category. So as you probably know, terahertz frequencies are somewhere between optical and electronic millimeter wave frequencies. And for these reasons that I mentioned in the next slide, both electronic and optical techniques have limitations to produce efficient terahertz terahertz waves in this range, and also for manipulating, detecting these waves. Also, there are some basic limitations. But before getting into those limitations, I want to say that there are some unique specifications for terahertz waves that make scientific community motivated to continue working in these fields. And there has been extensive advancements in the past 2 decades. And that's mainly listed here. So mainly it is because of rotational and vibrational frequency of most molecules and gases lying in this frequency region, allowing a very unique platform for non-invasive chemical identification. Also, the fact that a lot of optically opaque materials are more transparent at terahertz frequencies, that allows doing imaging and sensing in domains that optical waves and infrared waves have limitation getting there. And also, they're very low energy radiation compared to, for example, X-rays and optical frequencies. As a result, in terms of constant use of them in product development lines for medical imaging applications and biosensing applications, they have less chance for ionizing tissue or damaging and causing destruction in different products. And because of that, there are a lot of exciting applications that have been demonstrated. For example, in medical imaging, here is an image of skin cancer tumor. This is the visual image on top of the skin, and here is a terahertz image. Because water absorbs terahertz very strongly at specific wavelengths, you can see that you can get a very strong contrast in the image, better than optical wavelengths. Here is the visual image of a tooth, which has some early stage. You can see some early stages of decay in it. And here is the terahertz image. As you can see, the terahertz image again shows a very strong contrast. Actually, I'm sorry, this is the X-ray image. I said optical image. So in the very early stages of tooth decay, when no physical damage has happened to the tooth, X-ray cannot see any kind of erosion. But in reality, what is happening is that a new kind of lesion is forming in the tooth and does the erosion. And because it has a different water content, terahertz imaging can see that very clearly. And label-free genetic sensing, genetic testing has been demonstrated. Actually, when a single-stranded DNA hybridizes, its terahertz spectrum changes, so you can use it for label-free genetic testing. Actually, in security screening, I'm sure all of you have experienced airport security passing through the scanners that can see through the clothes. And those are really very low-frequency terahertz imagers. And if you really expand this technology to higher frequencies, you can get better resolutions. And if you get higher powers, you can imagine you can do this kind of imaging from remote distances. So that's an exciting area that brings a lot of funding to researchers in this field. In pharmaceutical industry, actually, this is a very exciting area that there are commercially available products used. There are two specific problems when you want to produce pharmaceutical products. First, when you build a capsule, you want to make sure the right thickness of coating is used in the capsule, because that affects how long it takes for the drug to get released in the body. And terahertz is in a very convenient range in terms of penetrating through these layers and also measuring the thicknesses with accuracy. Normally the way this is done without terahertz is an invasive way. You cut the capsule, some samples, and then you measure the thicknesses. But with terahertz, you can do that non-invasively. Another big problem in pharmaceutical industry is that you put the right chemical in the drug, but the chemical turns out to crystallize in different forms, which, again, it affects its solubility in water and its release time in body, so it's very important. And a lot of times with a lot of chemical sensing sensors, you cannot sense that. But with terahertz, since different crystalline forms gives you different rotational and vibrational frequencies for the molecule, the terahertz spectrum is obviously different. So again, in a non-invasive way, you can even see if you have a different kind of crystalline form, the right or wrong crystalline form. For industry quality control, actually, again, it's another exciting area that there are commercial products on that in product lines in order to see if the right thickness of a material is used, or in food industry in order to see the quality of crops and grains and their freshness is another area. And last but not the least, atmospheric studies and space industry is another area, which maybe I should have put it at the beginning because it is the very first application of terahertz technology. Actually, the oldest terahertz sensor, terahertz system, has been flying for the past 25 years with Earth observing satellite to detect specific spectral lines of gases which determine the health of the atmosphere and the ozone layer. If you look, for example, just for determining the OH line, which has a lot of information about the ozone layer, just for detecting that spectral line, this satellite is carrying a CO2 pump laser, which is gigantic. But at that time, it was the best solution. So you can imagine by more development in this technology and having more compact and high-performance sources, one can fit more equipment to observe atmospheric condition in future. So that being said, I have to say that, like the example I just gave here, a lot of these applications have been demonstrated through very bulky setups. A lot of them have been in lab environments where huge femtosecond lasers have been used. So although they're very exciting, but they're not yet in our everyday life because of the size and efficiency limitation that they have. So that's the area that a lot of groups, including my group, are working on. And in order to understand where this limitation is coming from, I want to go back to Maxwell's equation that describe anything about electromagnetic waves and see maybe from here we understand where these physical limitations are coming from. So now I want to think of a very basic operation that we need in any imaging or sensing system at terahertz, a terahertz source. We want to create an electromagnetic wave, so I want to understand what is the physical limitation here. The first two equations deal with static waves, so it has nothing to do with wave propagation, wave generation. Actually, the next equation also just deals with wave propagation. There is no magnetic monopole, so it cannot show us how terahertz generation is limited. Actually, it is the fourth Maxwell equation, which I have rewritten it in this funny form, that really shows where the fundamental physical limit is coming from. Actually, if you look at the conduction current and this displacement current, you'll see that these are the main mechanisms for terahertz generation in electronic and optical sources, and we can focus on each category and understand what is the fundamental physical limit there. Let's first start with the optical sources where displacement current is in charge of wave generation. A very simple source like a laser diode, like the one I'm holding in my hand, we have it available in our optical frequencies. It works excellent. So why not scaling the operation to operate at terahertz frequencies? Let's see how it operates. You have a forward bias PN junction. When you forward bias it, you have carriers accumulating here. They don't. They just stay in their own place. We don't have real conduction. That's why it is different than this mechanism. They just stay in their own place and resonate till they get recombined. And when they get recombined, they give out photon. Very simple operation. So why not getting the same concept, getting terahertz waves? The problem is here. In order to radiate a photon, the energy of the photon should be in the order of the bandgap energy. And the smallest bandgap energy that a natural material offers is 40 millielectron volt, which is equivalent to 10 terahertz. Below that, we don't have a natural material with that kind of bandgap energy, and that's why we cannot have a laser diode in that frequency range. Well, there are a lot of smart ways around it to solve that problem. You can use different trap levels that you can introduce into a semiconductor, or you can engineer quantum wells by stacking very thin layers of semiconductor and with different bandgap energy. And this way you can introduce new interband and intersubband energy levels, which are much closer to each other compared to a bandgap of a natural material. Well, that's the concept behind quantum cascade lasers, which are very exciting. But the problem is that as you start lasing at terahertz and you go to lower and lower frequencies, you reach to the range that even these interband energy level differences becomes comparable with thermal noise and phonon resonances in the lattice. So it becomes extremely hard to selectively inject carriers to predetermined energy levels. That's why usually these devices have to be cryogenically cooled, and they have some limitation with tuning. This is one way to generate terahertz waves, so we are not ruling it out. I'll keep it there, but at least we got a sense of the physical limit of the optical techniques. And by optical technique, I talk about a fundamental oscillator. So on the electronic technique, where conduction current is the mechanism behind radiation, I want to look at a very simplistic case of a solid-state circuit-based source. Let's say somehow magically on chip, without any limitation, we generate terahertz signal through a loop oscillator or other kind of oscillator, just at the very last stage of transistor that you want to dump this terahertz voltage on a junction of a transistor and create a current and pass it through antenna. Right here you have two major frequency limitations. First, the time that it takes for carriers to pass through the channel of the transistor cannot be zero. There's a finite time. And unfortunately, it cannot be shortened that much, even though now transistor channel lengths are reaching really to nanometer dimensions. The reason is that the speed of carriers in semiconductor is limited by scattering. You cannot just increase the voltage and get higher speeds. After some point, it is limited. And because of that, you have some frequency limitation here. And of course, any semiconductor solid-state device has parasitics. So even though you assume you have just one pole because of the parasitics, the transit time of the carriers and the pole coming from the parasitics just gives you a 1 over frequency square roll-off in your current that you can feed to this antenna, and the radiation from antenna has a quadratic relation with the current that gives you 1 over almost frequency to the power of 4 roll-off. That's why the electronic devices really degrade their power and efficiency as they go to higher frequency. So that's the limit here. So in fact, if you look at this was sources, if you look at detectors, you run into exactly the same problems. Either you want to make a detector electronic wave, then you're dealing with transit time and parasitic limitation, or you want to make it optical wave, like a photodetector, then you have to compete with thermal noise and phonon resonances, and then you have to cryogenically cool the device to be able to get the same performance. So while both communities, transistor and device communities and QCL communities, are coming with more much more innovative and brilliant, actually, ideas to improve the performance of their devices, the approach that I take in my group is different. Actually, we are sort of cheating. We say we have excellent optical sources already existing. Let's just find an efficient way to convert the energy to terahertz. And so in that sense, we're working on two different techniques. One is based on nonlinear optical techniques that I know there has been a lot of excellent work done here. But today I'm going to talk about another approach, which is based on photoconduction. And I'll explain why we find a lot of potential in this technique and how we are employing that to get high efficiency terahertz sources. Before then, just following the fundamental limitations that I showed here is a survey of different kind of sources that are available. As you can see, at lower frequency ranges, the electronic sources like impede diodes, gun diodes, different resonant tunneling diodes, their powers are dramatically increasing, and almost you can see the 1 over frequency to the power of 4, 3, something in that range roll-off. So there's for a good physical reason that you see this roll-off. And on the optical ranges, obviously the different optical sources become less and less efficient as they reach this frequency. And quantum cascade lasers are covering a good portion of the range, but we talked about temperature limitations of this technique. So photoconduction. Why are we excited about this technique? When did I start?
4:45.
Oh, okay. I thought half an hour I've been talking. Okay. So here I'm explaining the basic concept of photoconduction. And actually it is nothing new. It has been out there for almost 2 decades. But it's a very simple and low-risk way of generating terahertz waves. You build an ultra-fast photoconductor, which is basically a photodetector, not that different in concept. You pump it with an optical beam. This optical beam has a terahertz frequency component in its envelope. Either it's a short pulse in time domain, so it has broad frequency ranges at terahertz, or it is a 2 frequency offset CW beams at a terahertz frequency difference. So this photoconductor or photodetector, if it is ultra-fast enough, in an efficient way, it follows the envelope of the optical beam and creates a current that has the terahertz frequency components, feeds it to an antenna and creates radiation. And the antenna choice of different things I'm showing here is just arbitrary. There are several different designs that you can see in the literature. We usually want to place this device on a silicon lens because radiation tends to go to a higher dielectric constant substrate, so we prefer to collect most of it, 90%, more than 90% of it, from the backside of the substrate through a lens, and this way we can also do collimation and different wave shaping, beam shaping that we need. So the advantages. First, most of the burden, as I said, is already on the optical side, and we have excellent optical sources in both pulsed and CW operations, so already we are in very good shape to start. There is no threshold for radiation. As far as you pump the device with some optical beam, you get some terahertz wave. It might be too low to detect, but it is there. It's not like basic oscillators that have a threshold. And also, there is no physical limit in terms of efficiency. Like nonlinear optical techniques have Manley-Rowe limit. Here we don't have that limit. So fundamentally we can get 100% device efficiency from optics to terahertz. So that's great, but that being said, the existing devices have nowhere close to 100% efficiency. And we have studied the real physical reason behind it. Actually, the real physical reason can be seen here. In order to efficiently convert light waves to terahertz waves, the photons that land in the semiconductor have to generate electron holes, and electron holes have to see a bias electric field, and they have to be swept away to the antenna, where they can really efficiently give you radiation. The limitation is here. In order to have efficient terahertz radiation, the transit time of the carriers to the electrodes should be in a sub-picosecond time scale, a fraction of the terahertz cycle that we are interested in. Well, the problem is that the speed of the carriers in the semiconductor is limited by scattering. For example, for gallium arsenide, a typical material that you use, it is in the order of 10 to the 7 centimeter per second, which means if you want a sub-picosecond transit time, you're limited by 100 nanometer transport path length. Well, if you bring the electrodes close by 100 nanometer, first of all, capacitive loading is going to hurt you. The other thing is that optical absorption will be diffraction limited, so you'll reflect most of the light. You won't get much here. That's why conventional designs put the electrodes apart by several microns, but instead, in order to get ultra-fast response, they use a short carrier lifetime substrate. Literally, by that way, they just efficiently collect the carriers within about 100 nanometer distance from the electrode. They contribute efficiently to terahertz wave. The rest just recombine without much efficient contribution to terahertz wave. So by definition, it is low efficiency. So to address that problem, we thought, okay, if the diffraction limit is the problem, why not forming the contact electrodes in a form that we can couple light within the nanometer distances from the electrodes. And there are various ways we can do that. We can periodically form the sub-wavelength metallic structures to excite surface waves, and then this way we can couple light efficiently to these gaps between the electrodes. They can be even smaller than 100 nanometer. And by the right choice of metal, like gold, we can even go to the plasmonic domain, where light is tightly confined at the interface of semiconductor and metal, so most of the carriers will be generated very close to this interface. Well, what we're doing is that we cannot do much about speed of carriers. We just bring them right next to the electrode such that at least the transport path length is short, such that we can collect more of them. Here in this picture, I'm showing a plasmonic grating. We are not limited by grating. Any kind of periodic metallic structure, preferably with plasmonic properties at your optical wavelength, can be used to couple light right next to the electrodes. But as I show, we specifically like gratings because they have very unique properties, and by changing their aspect ratio, we can do cool things and increase efficiency of these devices. Before showing different generation of devices, we had a basic reason that you can couple light to a grating with deep sub-wavelength dimensions is because of the periodicity. You excite diffraction modes on top of the structure. For example, here, if you come with a TM mode, you excite diffraction modes. And these diffraction modes can now, since they're surface modes, they can efficiently couple to these sub-wavelength slab waveguide modes you can, for the waveguides you form by the gratings. And here, for example, you see for an arbitrary geometry, for different geometries compared to wavelength, you can excite the zeroth order resonance of these waveguides, first order, second order, third order. And that's the property we like about gratings, because we can change the aspect ratio of the grating, excite different order modes, and basically increase the coupling of the light right next to the electrode. I show that our first generation design uses the zeroth order mode, where the height of the electrodes is much smaller than wavelength, basically a surface plasmonic structure. With that, we get almost 2 orders of magnitude efficiency improvement, but still we have carriers which go deep to the substrate and we lose them. Then from there, we go all the way to another design with higher aspect ratio, which excites the 4th order resonance, second, third order resonance. And with that, we actually absorb more light, and that gives another order of magnitude enhancement compared to the initial design. So it's all about trapping light next to the electrode as much as we can. So here is the final element analysis of the first design we had. For this design, we were not targeting any specific wavelength, bandwidth, frequency. We just wanted to make 2 designs, one with the plasmonic structures, one without the plasmonic structures, and see what is the enhancement there. So we picked a bow-tie antenna. In one design, we had the plasmonic electrodes. In the other one, we didn't have. And we just made sure the radiation properties of these 2 antennas are the same, and both see the same parasitic from the device. So right here you can see in the conventional way that we don't have plasmonic electrodes, first of all, we cannot focus light better than diffraction limit. So if our measure is really how many carriers are at 100 nanometer distance from the electrode, here a very small portion is next to the electrode, and the rest is scattered. And in the plasmonic case, you have a tight confinement in both lateral and vertical direction, although we still lose some light here next to the electrode. So here, if one counts the number of photons which are in 100 nanometer distance from the electrode, in this case, you have 10 times more photons compared to here under the same illumination. So 10 times more photons within 100 nanometer distance, it means within a sub-picosecond time scale, we collect 10 times higher photocurrent. And since radiation has a quadratic relation, radiation power has a quadratic relation with current, it means it has to offer 2 orders of magnitude better efficiencies. Actually, we experimentally observed that. So here are the 2 designs that we fabricated. This is the one without plasmonic electrode. This is with plasmonic electrodes. And here are the results. This is the power of the plasmonic design based on different optical powers. And here is the power of the non-plasmonic design, which you see there is like 50 times enhancement by going plasmonic. And if you look at the photocurrent of the device, it is also enhanced by 7 times, exactly the quadratic relation that I mentioned. So the enhancement in the power is for a good reason, and that is because of a photocurrent enhancement. And that's again for a good reason. It's because more carriers are in a short distance from the electrode. So this was very exciting, and from this point we became more targeted looking at different frequencies, different operation regimes, and we implemented this design in different ways. This is a design that we're very excited about. For example, large area emitters are very popular for generating high power terahertz radiation. These are basically interdigitated electrodes placed on a photoabsorbing substrate. You pump it with ultra-fast light, and then just imagine these electrodes don't exist here. Then you separate electron holes from each other because of the bias in the substrate. You form a dipole moment, and that gives you radiation. But because this dipole moment is created in the substrate, and again, I repeat, the speed of carriers in the substrate is limited, the radiation is very weak because dipole moment is weak. So we said if we implement an array of these plasmonic antennas exactly in the same area where light lands, then we can quickly couple most of our electron holes to these plasmonic dipoles. And now the radiation happens on a metal, which is definitely a better radiator. It has a better impedance matching to free space. It gives you a stronger dipole moment. And we should get high radiation efficiency. So we are losing some of our area in this design because we have to shadow every other electrode, otherwise the radiation destructively combine. But even though we lose this area, and we have techniques to hopefully in the next design get rid of that, you can see that we get very high powers with very high efficiencies. At 150 milliwatt, we are getting around 3.6 milliwatt of terahertz power, and 150 milliwatt is the optical power. This is 2 orders of magnitude higher than conventional large area emitters, and this is again the same scheme, like you bring carriers very close to the electrode, it helps. So in this design, which is pumped by a femtosecond laser, you see you generate a very short terahertz pulse, which has frequency components extending 5 terahertz. We get around 100 dB signal to noise ratio. Actually, the bandwidth here is limited by our detection spectroscopy, time domain spectroscopy system, because we use lithium niobate as an electro-optic crystal. So here our bandwidth is limited by the loss in lithium niobate. So this is very promising. And this is a device with an area of 1 millimeter by 1 millimeter. Usually these large area emitters are centimeter by centimeter. So now we are very excited to fabricate this on large areas, and we will get such high energies that we are exploring nonlinear effects at terahertz domain. So we are very excited about prospects of it.
Could I ask a question?
Sure.
Is that the peak pulse power, or do you see how
Average.
average power?
Yep. Yeah, here is, we have the exact field measurements, but since we cannot focus waves that much, but already our calculations show megavolt per centimeter energies. And our femtosecond laser is not that high energy per pulse because rep rate is 80 megahertz. So now we want to try this device with some colleagues who have kilohertz rep rate femtosecond lasers, and there is where we are really hoping to see some nonlinear effects at terahertz. Okay, so this was the story with the plasmonic designs that are surface plasmonic design, and as I mentioned, still there are carriers which go deep to the substrate. We lose them. So to solve that, we go to higher order resonance mode of these gratings that can be available. So here might be a little bit different from the grating that I showed because it was fully filled with metal in the previous slide, but it was extremely hard to fabricate it. And then we realized in order to make these slab waveguides, we just need a metallic boundary condition. We don't need to fill the whole thing, and that made our fabrication much easier, and we implemented this design. Basically, nothing is different. I mean, here I'm showing a different design based on log spiral antenna, because it can give you much more bandwidth. The only thing we do is that at the input port of the antenna, we use this high aspect ratio design. So here, compared to the first generation, which was based on surface plasmon structures, you can see that although the previous design was already much better than the conventional designs, you can see this generation is much better because you're confining more light next to the electrode. So in order to quantify the enhancement we get by going from surface to 3D, we fabricated 2 identical designs, one with 2D plasmonic electrodes, one with 3D plasmonic electrodes, and we compared their operation under the same condition. So when you go to 3D, things become a little bit tricky. First of all, your transmission spectrum becomes very narrowband. So fabrication becomes very tricky. See, here, for example, for this geometry that we chose, you see we are exciting the second order, third order, fourth order resonance. Here, this order resonance is a little bit stronger because we intentionally chose our anti-reflection coding to be optimized for this wavelength. This is where our laser is. But here you can see this main peak can dramatically shift if we slightly change the height of this grating when we fabricate. So the fabrication is very delicate. For us, our we have a lot of limitation in terms of the wavelength of the laser. So we have to make sure the structure is built for that wavelength, otherwise the efficiency drops. So the height of the gratings are very precisely controlled during the process. And the process is basically two back-to-back etching processes. We want to use silicon dioxide as our hard mask, but first we have to pattern it with some nickel gratings to etch silicon dioxide. Now this is our hard mask. We etch gallium arsenide. Again, the fabrication is tricky because the slope of the sidewalls should be chosen such that when we deposit metal, we don't deposit too much on the sidewalls, otherwise liftoff is hard, or it is not too little such that we cannot get much coverage on the sidewalls. So after several arrangements, so we found the right slope, so then you lift off and you put the right anti-reflection coating layer on it. And here is the SEM picture of the cross-section of the device, which looks like tooth X-ray. So these are the gallium arsenide gratings. So they're in 70 to 100 nanometer range in terms of width. From top to bottom, the height is 40, exactly what we targeted. I'm not showing all the failure stories. We have other designs that are at wrong heights, and then you can see how the absorption peak shifts. But for the right height, you can see that the absorption peak is exactly at 800 nanometer, 70% that we expected, exactly as theoretical results were predicted. So now this is ready to go and get coupled to the antenna. So as I mentioned, we have two designs. One, the 3D electrodes are used. Another one, the 2D electrodes are used. And so here is a zoom-in picture exactly on the cathode and anode. And here is the close image, SEM image of the electrodes. Even from the top view, you can see metal coverage around the side of the gratings. So here is the comparison between the radiation power from the 2D design and 3D design, about an order of magnitude enhancement, which is exactly coming from the fact that we are collecting more carriers which are right next to the electrodes. And one thing we're very excited about is the power that we generate. Actually, here in this whole measurement, the optical pump power is 1.5 milliwatt. At 1.5 milliwatt optical power, we are generating 105 microwatt terahertz power. This is 7.5% optical to terahertz conversion efficiency, which we're very excited about. And if you think of it, around 30% of this is really just the reflection loss at the lens. About 85%, well, 100, so 15% loss is just coming from the efficiency of the antenna. So we are not really that far to make this efficiency very close to what the theoretical limit tells us. And we know still we are losing carriers which are deeper in the substrate, so we have some ideas how to improve that. And it works. But one thing that I have to mention is that although this efficiency is very high, but as you pump the device with higher optical powers, the efficiency drops because of the carrier screening. So I will show that larger area devices are solving that problem to even offer this higher efficiency at higher powers. And this specific design is very flexible in terms of increasing the area, because the plasmonic electrodes are a part of the input port of the antenna. They're not interdigitated, so you can increase the area without adding more parasitics to the design. One other thing I want to mention before getting to the next topic is that this multispectral behavior of these gratings is very exciting for us. So far I showed you a design which is optimized for 0th order mode, another design for the 3rd order or 4th order resonance mode. But we thought, why not designing a grating that at the same time it excites coupling modes at terahertz for the 0th order mode, where wavelength is much higher than height, but at the same time an optical mode by, I don't know, 3rd or 4th order resonance. So this way we can couple optics and terahertz at nanoscale at the same time, and then we can do optical palm terahertz probes studies at nanoscale in a very unique way. So the same design I showed, how it was allowing coupling of the 70% of the light. Here I'm showing the transmission of terahertz through it. You can see there is just 3 dB loss, which is not coming from the grating. It's coming from the Fresnel reflection from the backside of the substrate. So we are efficiently coupling terahertz at the same time optics to this grating, and we're very excited about this, because now we can do optical pump terahertz probe studies at nanoscale. And for example, we're applying it to measuring the ballistic and quasi-ballistic mobility of carriers at nanoscale, where the quantum effects, interface effects, all of them are in place. Exactly realistic scenario like transistor. None of the ensemble techniques which look at the mobility at nanoscale include all these interface and quantum effects. So we're very excited about that, and we are looking at indium gallium arsenide, which is a high mobility semiconductor, and a lot of industries wonder how embedding them in transistors can help increasing the speed. So we want to really see where mobilities are. Also, I have to add that the techniques that I mentioned in terms of increasing, so I'm switching gears, I go back to the same plasmonic technique helping terahertz devices. So I mentioned that using these plasmonic electrodes help increasing the efficiency of terahertz sources, but they also help with increasing the detection sensitivity of terahertz detectors. If you're familiar with photoconductive devices, you would know that the same device can be used for generation and detection, both. So for a source, we had to bias our photoconductor, pump it with the optical beam, and generate terahertz waves. If you want to use it as a detector, you don't bias it. Actually, you apply 0 bias. You receive terahertz wave, and the terahertz field will bias the device, and when at the same time your optical beam lands, it gives you a current that you can measure. So we thought, okay, if carrier concentration right next to the electrode can be enhanced by using these plasmonic structures, so the output current should be also enhanced in ultra-fast way. But the thing is that here, because the current is linearly related to the power, the enhancement factors here that we get are not quadratic, are linear, but it is still enhancing. This is a proof of concept experiment we did. For this experiment, we didn't have a very high frequency terahertz source. You can see how the bandwidth of the source is as a function of frequency. And it's a commercially available source. So here you see the signal we detect with our plasmonic detector and the non-plasmonic detector, and you can see 30 times enhancement. Here the red curve is multiplied by 5. And in the spectrum, you see exactly the same enhancement over wideband. We were not sure if this is the noise increase at the same time. So we did some noise analysis. We turned off the terahertz signal, and the signal level at the output turned out to be at the same level. So this is not noise increase, although this is really the noise of the source we're detecting, but the increase in the level is just increase in the detection sensitivity of the device. And we predict that because the noise of these photoconductive devices are coming mainly from shot noise, and shot noise is basically not related to the architecture that we are using. As a result, this terahertz time enhancement in responsivity is really terahertz time enhancement in sensitivity. And remember, this design, the design used for this study was a 2D plasmonic structure, so we can imagine to have better sensitivities for the 3D design. So this is an area that I wanted to mention. It's an ongoing research. We haven't implemented it. So now that our powers and sensitivities are so high, we are now, and we have actually, I have to mention, we have, I showed a lot of results with gallium arsenide. We have also made our design compatible to 1550 nanometer wavelength when you use indium gallium arsenide. So we're building this endoscopy system where we place an array of sources and detectors, like the large area devices that I showed, at the tip of an endoscope. And we did a lot of study on commercially available endoscopy systems. We're lucky that a lot of them already have an empty channel made available for different, basically, applications. And another good thing is that already a CCD camera or different kind of optical cameras are there, so we can basically capture the visual image and terahertz image at the same time. So this is an area that we are working on, and really, so we are thinking about coupling femtosecond light to both sources and detectors, and if we have a good way to control the frequency of pumping and probing, we can scan the image in a real tissue very fast. And since these are pulsed devices, then by looking at the reflection of the pulse from tissue, we can really see the 3D profile of the tissue. We're very excited about it. So as I mentioned, we have also made our designs compatible with 1550 nanometer wavelength. Here is one of the designs. We use erbium arsenide, indium gallium arsenide. Erbium arsenide gives us the short carrier lifetime properties that we need. And here we wanted to see if this enhancement also exists in photomixing mode. Remember, terahertz signal basically follows just the envelope of the optical beam. So I showed a lot of results when we pump it with a pulse, but you can pump it with 2 CW lasers. So here we had 2 1550 CW lasers, and we pumped we actually picked a photomixer that is conventionally used. It's based on interdigitated electrodes. We made another one equivalent to that in the sense that we used the same antenna, we designed it to have the same parasitics, and we saw also similar enhancement factors. Depending on the optical pump power, we are seeing somewhere between 1 to 2 orders of magnitude enhancement in optical to terahertz conversion efficiency. In this work, we just wanted to somehow quantify the enhancement factor and see if it is the same as what we see in pulse domain. We didn't really optimize it for high power, but then following that, this design was optimized for high power by adjusting the right gap between the electrodes and electrode sizes. Here you see the antenna, log spiral antenna, which is very broadband, and the plasmonic electrodes are at the input port of the antenna. Here you see that we get a very broad band terahertz radiation by just slightly tuning the frequency difference of the lasers, and different optical powers give different terahertz levels. At 1 terahertz, we are getting about 1 milliwatt of CW power, and this is so powerful that actually the main limit we are dealing with is really the thermal breakdown we have in these devices, especially indium gallium arsenide has a very poor thermal conductivity. So in order to bypass that problem, we're duty cycling on our optical beam. So when I say 1 milliwatt, it is 1 milliwatt in each cycle. And one might say, okay, if you duty cycle it, you might change the line width of your radiation. Actually, not really. You can choose your rep rate and also the duty cycle such that you don't really ruin your line width. For example, For this experiment, we were using 1 megahertz rep rate. And here you see for different duty cycles we are not really changing the line width compared to the center wavelength much. But one might say, I want to do gas sensing. I want kilohertz line widths. Well, you can just change the rep rate. If you go to 0.1 megahertz, you can get there. So it is just for thermal control. And if the device is fabricated on a larger area, that can be solved. Like other techniques, we have a lot of flexibility. Once you have an antenna-coupled device, you can use arrays of them for going to higher powers. Here we use an array of 3 by 3 of these plasmonic sources. Also once you go to array, now you have this flexibility in changing the phase of different elements and now doing beam steering. So that's another exciting thing we can do with these devices. Again, just because we have excellent optical sources, and optical sources can be tuned in different ways. And here you see, like, we are able to get to 2 milliwatts. For example, for these photomixers pumped at 1550, another new area, new application we are targeting is for high data rate communication. This is an ongoing work where the data that we want to transmit will be coded on the optical signal, and then will be pumped to these high-power photomixers, and then we can even use 2 cross-polarizations to multiplex data, and then use a nonlinear technique like a Schottky diode for detecting it. So what we are targeting now, this hasn't been achieved yet, but looks feasible, is 160 gigabit per second over 10 meter lengths. So we are thinking about using this for a backbone of supercomputers or for low-range data communication. So within a short time that I have, I quickly, briefly mention about other thrusts in my group. I didn't have time to mention about other terahertz sources that we work on based on nonlinear optical phenomena, and also other detectors we work on based on quantum wells and quantum dots. But I want to mention that we are also working on passive terahertz devices. Sometimes we forget that when you want to build a system, it's not always source and detector. There are lots of other components that for optics and electronics people might be trivial, but we have to struggle at terahertz frequencies. So these include intensity modulators, phase modulators, passive beam steering devices, filters that are a big challenge, because if you go back and look at a lot of techniques that are used in optics and electronics for doing these passive operations, if you want to scale the same thing at terahertz, either you run into material limitation, you won't have the same properties, or the scale of the device will end up to be a very unrealistic scale to implement. That's why metamaterials were very exciting. There has been a lot of improvement in this area because you can engineer what natural materials don't offer to you. So here I'm going to focus all my discussion on just intensity modulators, but please check our work on other types of devices. These are some metamaterial-based intensity modulators that are built at terahertz frequencies. Basically, you make a resonant metamaterial and like a split ring resonator, and somehow, either by introducing carriers in the substrate or depleting the substrate, or by changing the temperature in a phase change material like vanadium dioxide, or by mechanically changing the shape of the split ring resonator relative to the incident terahertz wave, you can shift the resonance and then see modulation at the frequency of interest. These are all exciting, but the problem is that a lot of terahertz systems are broadband. They're pulse-based, like the ones I mentioned. So these are very narrowband. So that's a main limitation. So that's something that my group has specifically looked into. So this is a solution we offered. We said, okay, let's say we have 2 arrays of capacitive mesh filters, basically separated metallic structures in sub-wavelength dimension. So these devices act like a low-pass filter where cutoff frequency is determined by the feature size. So if you make feature size very small, it is a very broadband low-pass filter. So we said, what if we built these two low-pass filters in a configuration that we can mechanically put them in touch. When they touch each other, now you create these current loops, and then it all of a sudden becomes an inductive mesh filter. And the inductive mesh filter actually is a very broadband high-pass filter, or depending on the geometry, it can be band-pass filter. So you can basically change your scattering parameters from a very broadband low-pass to a very broadband bandpass or high-pass filter, and for a very broad range of frequencies you can see high modulation. And you can extend this bandwidth if you make this feature size smaller and smaller. So for implementing this, we went to MEMS. This is the device that we implemented. So this is an array that terahertz is incident on it. Here I'm focusing on just one element. There is a freestanding cantilever. Actually, it's not a cantilever. It's a fixed beam on these two anchors. And underneath there are these electrodes with this specific shape. So if your terahertz polarization is in this direction, actually in X direction, normal to this beam, then the geometry of the structure is deep sub-wavelength at terahertz. So, and they are just discontinued from each other, so it cannot excite currents. So it acts like a broadband low-pass filter. As soon as you actuate this switch, it goes in contact with these electrodes. And now if you imagine this is connected to the next device and next device, you have these current loops formed. And now it changes the scattering parameters to high-pass filter. And here is what theoretically you would expect. Here I'm showing a much more broadband bandwidth that we need to show you that the bandwidth is really related to feature size, but if you work with conventional TDS systems between 0 to 1.5 or 2 terahertz, you can get very broadband, large modulation depth. So we have, and here is another visual image of how wave interacts with this structure. This is the cross-section. If these switches are separated from each other, you can have terahertz wave pass efficiently. In the other case, they have to curve and go around. Basically, nothing can pass. And I have to also mention that the displacement we need for this to happen is in the order of few tens of nanometer. We might leave more area for, in case the device is on vibration, to make sure they don't abruptly contact each other. But as a result, it can be potentially fast. But still, it's MEMS, so it cannot be super fast. I don't get into the details of fabrication. It was pretty complicated. Basically, you have to use different layers of photoresist and different oxides in order to let this thing basically float in the right height. And you have to use different layers of metal and deposit them in different ways that stress is canceled. Anyways, I won't get into that. So we fabricated the devices and tested them in a general time domain terahertz spectroscopy system. We had a broadband terahertz pulse passing through the device, and then we look at the transmitted signal through an electro-optic detection technique. And here are the results. So here you see the array of these MEMS switches, and here is closer view. You see the anchors, and these are the electrodes. So the blue curve shows the pulse before actuation. The red curve shows the pulse. This is the electric field of the pulse after actuation. And here is the spectrum, like Fourier transform of the transmitted spectrum for the power. So these dips actually are coming from the apertures we use to focus terahertz on the device. To get a good yield, we are focusing terahertz on a millimeter by millimeter area, so you see these absorption dips. But here I'm translating, and the overall waveform is coming from our source, so that doesn't mean much. What is important here, modulation depth, is the ratio of the maximum to minimum, and here is the modulation depth. You can see that over the bandwidth of 1.5 terahertz, we're getting even more than 70% modulation depth, which is even higher than the modulation depth of the resonant metamaterials. So this is a very exciting opportunity for us. And so in the future, what we want to do, and here is a limitation of the device, is the speed, obviously. These are MEMS devices, so our frequency is limited to few tens of kilohertz. So the limitation we see here is that, first of all, we want to extend the bandwidth even more. So we have to shrink the feature size. For that, MEMS designs are having some problem. Also, the speed, we would like to go faster. Again, conventional MEMS design has a problem. So for this, to solve these problems, we have started a collaboration with a group who make these graphene membranes. So with graphene, you can basically actuate the membranes pretty fast, and then you can make the feature size very small. So we want to replicate similar idea on graphene. Well, graphene gives us its own limitations, so we have to deal with it. But anyways, the prospects are good. And at the end of the day, this is a silicon-based, fully integrated design. A lot of metamaterials I showed need an external light source to basically excite the device or change the temperature. So as a result, it can be used for large arrays, for example, for single pixel terahertz cameras through compressive sensing algorithms. So it can be useful in those kind of applications. Again, I don't have time, but we are working on different kinds of metamaterials which do phase modulation. So we have recently shown very high phase modulation through a reconfigurable metamaterial based on vanadium dioxide, which is a phase change material, but not through an optical technique. Sorry, not through a thermal reconfiguration, through an electronic reconfiguration, so it is fast. And also based on that, we have seen very strong beam steering through an array of those phase modulators. So I believe metamaterials and metasurfaces have a lot of promise, specifically in terahertz frequency range where natural materials have their limitations. So a lot of limitations we have these days will be solved in the future. We'll have better passive and active terahertz devices to have more realistic terahertz systems. So in summary, what I had time to discuss was use of plasmonics for enhancing the radiation power and efficiency of photoconductive terahertz sources. It looks very promising to offer close to 100% efficiency for these devices. For detection sensitivity, it looks not as promising, but still it has significant impact. We showed 30 times enhancement in detection sensitivity. Also, these plasmonic structures make interesting opportunities like multi-spectral pump probe studies at nanoscale. And also, I specifically talked about MEMS reconfigurable metamaterials for terahertz intensity modulation, but there are other areas that we're working on. Please feel free to check our website where we have more detailed information and publications. And at the end of the day, the research is done by my students. I just talk about it, so I want to thank them. And my collaborators, we have a lot of collaboration on the material side because sometimes we need specialty materials. And also, I'm looking for new collaborations here on the laser side. At the end of the day, the terahertz sources and detectors we make are very compact, but the main size and efficiency of the system is coming from lasers, so having flexibility in a collaboration to set the parameters right is something I really look forward to. And also I want to thank our sponsors and would be happy to take your questions.